We have discussed the equivalence principle in our previous lecture. And you know, the equivalence principle is actually the very strong mathematical tool for general relativity. But you have explained the equivalence principle in that video by argument, by logic. But you know, any principle or any law of physics is treated valid only when we test it experimentally. So, what will be the experimental test for the equivalence principle? A well-known Hungarian physicist named Baron Lorand Eotvos in the late 19th century, that is 1896, and again in the beginning of the 20th century, that is 1908, actually performed a very ingenious experiment to test the equivalence principle. So this experiment is known as Eotvos experiment, and this is of great importance in general relativity because it gives the experimental confirmation of the principle of equivalence. Okay. So in this lecture we are going to discuss this Eotvos experiment in very detail, and we will learn how this experiment confirms that the gravitational mass and the inertial mass are equivalent to one another. Or you can say that the aim of this experiment is to test whether inertial mass and gravitational mass are equivalent or not. When you say that the aim of this experiment is to test the equivalence of inertial and gravitational mass, it means you are saying that whether different materials fall at the same rate in gravitational field regardless of their composition. Okay. So this is the aim of this particular experiment. Okay. Since we are going to discuss experiments, so definitely we will divide our lecture in different parts, because you know, first of all, we know what is the purpose, what is the aim, what is the objective of this experiment. And after that, we will discuss the apparatus, the experimental setup, and how experiment is done, what is the actual method, and finally we calculate the required quantity. Okay. So as I have told you that the objective or aim of this experiment was to test the equivalence of inertial mass and gravitational mass. And finally you will learn after this the discussion of this experiment that actually the gravitational and the inertial masses are equivalent to one another, or they are proportional to each other. Okay. And flatly you also say that gravitational mass and the inertial masses are equal of a body. Now let us see how this experiment was performed, what was the experimental setup. Actually in this figure I have shown the schematic diagram of the apparatus used in this experiment. And from this figure you can see the most important part of this apparatus is a torsion balance. So torsion balance is the most important part of this apparatus. And in this torsion balance, actually the Eotvos used a sensitive torsion balance which consisted of a horizontal rod, as you can see here. This is the horizontal rod, and from at the two ends, let us say and A and B, the two masses are connected, and you can say that two materials are connected. I have marked the first mass by 1 and another by 2. Okay, and these are actually connected at the two ends of the horizontal rod. In fact, it is assumed that this rod is in equilibrium, both in translational and rotational equilibrium, and therefore the rod remains horizontal. Okay. Now, the another important part of the this apparatus, you can see here that this rod is actually suspended by a torsion wire, or you can say metallic wire, which I have shown here, and from this connecting by this torsion wire, this rod is kept horizontal. Now the another part of this apparatus is test masses. Test masses. As I have told you just now that this 1 and 2 are actually the test masses. Okay, and these test masses are actually suspended at the two ends of the horizontal rod. In fact, these masses are made up of different materials like copper, platinum, or you may also take water-filled containers. Okay, and they are attached at the two ends of this rod. Okay. Now, in fact, the idea of Eotvos was that if Earth's gravity pulled differently on the two materials, that is, if their gravitational and inertial masses were not equivalent, then the rod would twist. This was the idea. If these two masses will be pulled differently by the Earth's gravitational field, then there will be a twist in the rod. This was the aim of this experiment, that the rod get twisted or not. Okay. In fact, for your convenience, I have mentioned all these facts here. You can see the experimental setup shown in this figure is shown schematically in this figure, and the first important part of the apparatus is torsion balance, another is test masses. Okay, and what was the idea behind this, I have mentioned here. Okay, now we will see what was how this experiment was actually performed. Let us see. In fact, this apparatus was carefully isolated from other influences. When you say other influences, that means the apparatus was actually kept isolated from the effect of temperature changes, from the air currents. Okay, so this rod with the attached mass are kept inside a cabin, and this cabin is actually made up of insulator, so that there will be no effect of the change in temperature of the surrounding on this. Okay, and also this will be unaffected from the air current. Okay, now actually the entire device was rotated, as I have shown here by this arrowhead, in either in anti-clockwise sense or in clockwise sense. Okay, and if after the rotation of the device any twisting of the wire, that is any torque developed, was carefully measured. Okay, in fact, what was the reason of measuring this torque? In fact, the Eotvos was looking for difference in the gravitational acceleration acting on the materials. But surprisingly, he observed that there is no measurable difference in the acceleration of the test masses. Okay? In fact, the acceleration of both of the test masses was found equal. So I have mentioned here this method. The apparatus was carefully isolated from other influences like temperature changes, air currents, etc. Okay? And the entire device was rotated, and any twisting of the wire, that is torque, was carefully measured. In fact, he looked for differences in the gravitational acceleration acting on different materials, but no measurable difference was observed in the acceleration of the test masses. Okay? So this was this is the experimental detail. Okay? Now we will prove the equivalence of gravitational and inertial mass on the basis of this experiment by analytical method, or you can say by proper calculation. You can show that gravitational mass is just proportional to the inertial mass of a body or a material. And for this, for proving this fact, let us see the free body diagram of the system shown in the experiment. You can see this is your rod, let us say AB, okay, and at the end A, the first body of gravitational mass mg1 is connected, and at the second end you can see the another body is connected whose gravitational mass is mg2. Okay, here we are talking about the gravitational mass of the object, because we will define the gravitational force acting on these two masses, and for that you have to consider the gravitational masses of the two objects. Okay, so the gravitational mass of the first object I have considered mg1, and the gravitational mass of the second object has been considered mg2. And so what will be the force of gravity acting on the first body or first mass? You can easily say that is weight of the first mass will be simply the product of the gravitational mass of the body times acceleration due to gravity, small g. So mg1 times small g, which is actually the acceleration due to gravity or gravitational field of the earth, that is the weight of this first object. And similarly, the weight of the second object or the force of gravity acting on the second object is mg2 times small g. Okay? Now for calculation, we consider this point O, where this rod is suspended by this torsion wire as origin. And as we will make our calculation in 3 dimensions, so let us set up a rectangular coordinate system here, taking the y-axis along the rod and x and z-axis as shown in figure. This is actually a right-handed coordinate system. And we also consider that the first body is at a distance L1 from O, that is, we consider that this OA is equal to L1 and OB is equal to L2. In general, if the masses of the two bodies will be different, then definitely L1 will be different from L2, because if the rod is kept in equilibrium position, both in translational and rotational equilibrium, then the tension developed in this wire must balance the forces acting in downward direction. Okay, so this point must be the center of mass of this system. Okay, and as in case of two unequal masses, the center of mass is not at the midpoint, it is closer to the heavier mass. Okay, so in general L1 and L2 will be different. Okay, so these are the gravitational forces acting on the two bodies. But as we are calculating this, we are actually we are going to discuss this problem in the Earth's gravitational field. And you know, Earth is a rotating object. So in Earth's frame, these objects will also experience the fictitious force, that is the centrifugal force. And for this, let us see here, I have shown in this figure, this is your Earth, and let us consider the two masses 1 and 2 are here. I have shown in this figure. And the place where these two masses are located, that is at a latitude theta. You know, this line will be equator. Okay, this is equator, and the angle made by this radius vector, let us say OP, with this equator, which is theta, that is called latitude of the place P. So we have considered that these two masses are at a place whose latitude is theta. Okay, and our Earth is rotating about its polar axis with angular velocity, let us say a small omega. Okay, now if you consider that C1 is the centrifugal force. What is C1? This is centrifugal force acting on the first mass, and C2 is the centrifugal force acting on the second mass. As you can see, since the radius capital R of the Earth is very large in comparison to the length of this rod, so we can treat that both masses are at the same place at the latitude theta. Okay, and both will describe this dotted circle whose radius will be what? In fact, if you take this point as Q, then this PQ is equal to a small r, and this will be equal to r cos theta, and this is the radius of the circle described by these masses M1 and M2. Okay, so the centrifugal forces acting on the first mass, if it is C1, what will be this? You know the well-known formula for the centrifugal force, that is defined as m omega square times r, where r is the radius of the circle. But here, in terms of radius of the Earth, capital R, this small r is r cos theta. So C1 will be m omega square capital R cos theta. Okay. But now, what should be this m? Because you are now considering applying the Newtonian mechanics here for finding this centrifugal force. So now, at the place of mass of the first object, you will have to write the inertial mass of the first object. So if we consider that mi1, this is the inertial mass of the first object, then the centrifugal force acting on the first mass will be written as mi1 omega square into r into cos theta. And similarly, if you want to write the expression for the centrifugal force acting on mass 2, then that will be simply mi2 times this much. Only instead of mi1, now you will have to write mi2, which will be the inertial mass of the second object. In fact, in this figure, I have shown that this is the centrifugal force C1 acting on A, and this is the centrifugal force C2 acting on B. So, neglecting all other forces, okay, you can say that two forces are acting on this body 1 and 2. First one is the force of gravity, another is the centrifugal force. Okay. Now, this rod is in equilibrium. That is, you can say that it is in rotational equilibrium. So, if you will take the moment of the forces acting on the body along the x-axis, the total moment of force or the total torque acting on this system must be equal to 0 if it is in rotational equilibrium. Okay. So let us see now this calculation I have made here. I have considered that this mg1 is the gravitational mass of body 1 and mg2 is the gravitational mass of body 2. mi1, this is inertial mass of body 1, and mi2, this is inertial mass of body 2. Okay. And as we have seen in the free body diagram there, that this mg1 times g, a small g, this is weight of the body 1, or you can say this is the force of gravity acting on body 1. And we have considered that this C1, which is equal to mi1 omega square r cos theta, this is the centrifugal force acting on this first object. And from here you can see, since we have placed the object at a certain place, so this theta will be constant. Omega, which is angular velocity of the earth, and r is the radius of the earth, both are constant. So you can say that if at the same place different objects will be used in this experiment, then this centrifugal force will be different due to the different value of mi1. Therefore, this you can see here that this centrifugal force is proportional to the inertial mass, that is centrifugal force acting on the first object, that is proportional to mass of the first object. Okay. Now, in a similar manner, you can say that this mg2 times g is the weight of the second body. This is the force of gravity acting on the second body in downward direction. And we have considered that C2 is the centrifugal force acting on this second body. And C2 will be given by mi2 omega square r cos theta. So you can see that C2 is directly proportional to mi2. Okay. Now, as I have told you that this arrangement is so made that the moments about x-axis get balanced. So you can see this figure. The moment of the force m1g, the perpendicular distance of the force mg1 times small g from this point O is L1. So when you will multiply L1 by mg1 times g, you will get the moment of this force of gravity or torque due to this. And you can see, since position vector r will be in this direction and as torque is r cross f, so the sense of this torque will be anti-clockwise. In this sense, this torque will act. Okay. And now take the component of this C1 in z direction. We will take component of C1 in z direction. You can see here. If we consider that this is C1z, then the torque due to this C1 about O, okay, or along x-axis, you can with respect to x-axis, that will be equal to again L1 times C1z, because the torque of this C1 in the, the component of C1 in this y direction will be C1y, and with respect to this x-axis, this component will constitute no torque, because then the position vector and the force vector will be on the same line, so r cross f will be 0. So only this C1z constitute torque due to C1 about the x-axis. Okay, and therefore, and you can see what will be the sense, since this is the direction of position vector and this is the direction of force, so r cross f will be now in the clockwise sense. So the sense of torque due to force of gravity and due to the centrifugal force acting on the first body are just in opposite direction. So the net torque acting on the first body will be what? That will be L1 times mg1 times small g minus c1z. Okay. Now in the similar manner you can see here there is another body of mass m2g, and the force of gravity acting on it is mg2 and times small g, and this perpendicular distance is L2. And again you have seen that this is the centrifugal force acting on it, and its component will be in this direction. This will be C2z. Okay. Again you can see here that the torque act due to this mg2 times small g, this will be L2 times mg2 times small g, and torque due to the centrifugal force C2 about O will be simply equal to torque due to its z component, and sense of both of this torque acting on the second body are just opposite, so that will be L2 times mg2 times small g minus C2z. Actually this torque acting on body 1 balances the torque acting on body 2, so both are actually equal and opposite. So I have mentioned here only the magnitude. So the magnitude of the net torque acting on first body is equal to magnitude of the torque acting on the second body. But if you will actually find the torque vector, these two vectors will be just in opposite direction, so their vector sum will be 0, and and we say that the moments about x-axis is gate balanced. Now from this equation you can see, if you try to find the ratio of L1 and L2, L1 over L2, that will be simply equal to mg2 times small g minus c2z over mg1 times small g minus c1z. Okay. Now we will try to find the torque about the z-axis. As you know, this mg1 times g and mg2 times g both are acting on z-axis. So torque due to these force of gravity about z-axis will be 0. But the torque due to the centrifugal force acting on the two objects about the z-axis will be not 0. This is C1, this is C2. These are the centrifugal forces acting on this body 1 and body 2. And now you are talking about the torque about z-axis. Okay. Now you can see the z component of C1 is C1z. This is parallel to z-axis. Z component of C2 is C2z. This is parallel to z-axis. So the torque due to components C1z and C2z about z-axis will be 0. But what is the x component of this C1 and C2. If you consider that the x component of C1 is C1x and x component of C2 is C2x, okay, C2x, then these components are perpendicular to this z-axis, and then you can find the torque of the of C1 and C2 about z-axis that will be constituted only by their x components, because the torque due to the z components of C1 and C2 about z-axis will be 0. So if you consider that tau z is the net torque acting on this system, then that will be L1 times C1x minus L2 times C2x. Why minus? Because the sense of the torque acting on first body and second body are just opposite to one another. Okay. Now, if you consider that the torque about the z-axis acting on this system is 0, then you can write L1 times C1x minus L2 times C2x, that will be 0. And therefore, L1 times C1x is equal to L2 times C2x. And so, you can say that L1 over L2 is equal to C2x over C1x. Okay. Now, you can see that equation 1 defines the ratio of L1 and L2. And equation 2 also defines the ratio of L1 and L2. But equation 2 is valid when we have assumed that tau z is equal to 0. So, if tau z is equal to 0, then you can equate the RHS of equation number 2 and that of equation 1. Okay. So, now let us equate it. So, you can see tau z is equal to 0 if and only if, this sign is for if and only if, mg2 times small g minus c2z over mg1 times small g minus c1z, that is equal to c2x over c1x. But as we have seen earlier that C1 is proportional to mi1 and C2 is proportional to mi2. It means the centrifugal force acting on the first body is proportional to inertial mass of the first body, and the centrifugal force acting on the second body is proportional to inertial mass of the second body. So its x component will be also proportional to these masses. So you can say that C2x by C1x must be equal to mi2 over mi1. Okay. So in this equation 3, instead of C2x over C1x, now you can write mi2 over mi1. Okay. So our result is mg2 times small g minus c2z over mg1 times small g minus c1z, and that is equal to mi2 over mi1. Okay. Now let us simplify this result to some extent. You can see, if you bring this factor mg1 times small g minus c1z in numerator and divide it by mi1, then this will be equal to mg2 times small g minus c2z over mi2. Okay. Now divide both the terms in numerator by this mi1 separately. So this will be mg1 by mi1 times small g minus c1z by mi1, and that is equal to mg2 by mi2 times small g minus c2z over mi2. Now these two terms are identical and these two terms are also identical. So let us arrange the terms. bring this term in RHS, first term in RHS in LHS, and the second term in LHS in RHS. Let us make interchange. So after interchanging these terms, you can see this will be mg1 by mi1 minus mg2 by mi2 times small g, and that is equal to c1z over mi1 minus c2z over mi2. But as you have seen earlier, that this c1z is proportional to mi1. Okay? C1z is proportional to mi1. Okay? And therefore c1z by mi1, let us say this will be equal to a constant, and this constant is, let us say, k. Let us say. Similarly, c2z is proportional to mi2. So c2z over mi2, this will be also a constant k. Therefore, this term and this term will be equal, and therefore when you will subtract one term from another, your result will be 0. Okay? So I have written here that this will be 0 because c1z is proportional to mi1 and c2z is proportional to mi2. So finally we get that mg1 over mi1. mg1, you know, this is the gravitational mass of the first object. mi1 is the inertial mass of the first object. And mg2 over mi2, that is equal to 0. So you can say that mg1 by mi1 is equal to mg2 by mi2. It means you can say that gravitational mass mg is proportional to the inertial mass mi. And this was actually to prove this fact was actually the aim of this experiment. So finally you can see that Eotvos results confirm that gravitational mass is proportional to inertial mass to a very high precision of the order of 1 part in 10 to the power 9 in later improvements. As you have seen, firstly this experiment was performed in 1896, and after some year in 1908, Eotvos himself modified his experiment and then performed the experiment with high precision, and it was found that the gravitational mass and the inertial mass of a object are actually equivalent to one another, or flatly you can say that both are equal. So in this way we have clearly understand what is this Eotvos experiment, and how this experiment actually confirmed the equivalence principle. Everything is now clear to you, as I think. Okay, thank you very much.